Hey everyone, welcome back to another DIYson Build Log where I document my process as I attempt to build an open source version of the Dyson Lightcycle lamp. After a couple of build logs pushing the limits of my electronic skills, I am back in my comfort zone and working on some tricky mechanical components on the lamp. In the last build log, I introduced the SuperTrack, which is an experimental power delivery method in the form of a long PCB that's hidden within the aluminum rails. Proof of concept testing from that build log suggests that this solution is possible in theory. But right now, my highest priority is putting that theory to the test with some real-world SuperTrack stress testing. Stress testing for me involves using the DIYson over an extended period of time and basically treating it like any old lamp and just seeing how it performs and if it holds up. So for the first time, I'm assembling all the latest components into this bleeding-edge, state-of-the-art DIYson prototype. And I have to say, I love the way the SuperTracks look in this prototype. I love that from many different angles, the entire power delivery solution is just completely hidden. And I find that when the SuperTracks are exposed, they have this sleek and industrial look that is totally reminiscent of the original Dyson design and something that drew me to it in the first place. I'm a huge fan of this, but as cool as this prototype is looking to me right now, it's far from finished. In fact, I can't even turn it on for more than a few seconds without some serious thermal disasters. And this is because I still don't have a good solution for mounting and cooling the LED, which right now is just floating around freely in the housing. So in this build log, what I want to do is get the LED securely mounted to the horizontal arm and find a way to keep it cool enough that I can leave it powered on for like a couple of hours. If I can do this, I'll finally be able to stress test the SuperTracks and see if they have any real-world potential. This is a topic that I've visited before, and on the surface, mounting the LED does seem straightforward, but as usual, there are a couple of hidden constraints here. This isn't just any ordinary LED we're working with. This little chip can put out over 12 watts of power at max brightness, and that kind of power generates significant heat. At extreme temperatures, the plastic housing around the LED could just melt, or the LED could just fail outright. But below those extreme temperatures, there's also good reason for me to keep the chip temperature as low as I possibly can, because as the chip gets hotter and hotter, it requires more input power to achieve the same output brightness. So cooling is essential for high efficiency. Beyond that, as with everything on the DIYson, space around the LED is really, really scarce, and whatever solution I arrive at will have to be super compact and super tidy. My first attempt at this was inspired by the real Dyson, and I got really fixated on this idea of using a heat pipe to pull heat away from the LED as quickly and efficiently as possible. I became even more insistent once I found this off-the-shelf heat pipe that fits perfectly within the channel of the aluminum rail. My plan was to pair this heat pipe with a custom mount that was machined or 3D printed in metal, which integrated the heat pipe in a little channel and screwed into the end of the horizontal arm like this. I'm running into a lot of problems with this solution. First off, custom 3D metal parts are very expensive and I have to custom order them. The parts are inconsistent and prone to unpredictable shrinking and warping, and the steel material I've selected is a relatively poor thermal conductor. And then on top of all that, even if I was able to overcome all of these issues, I would still have to permanently glue the heat pipe to the aluminum rail with something like thermal epoxy, which would be messy, imprecise, and it would make future updates a bit of a headache. I think it's time to say goodbye to this idea, and as hard as it is, I'm going to start over from the beginning. When I think about my dream solution for this part, which is something I do more than I'm willing to admit publicly, it's always made of copper. To me, copper represents this perfect mix of strength, thermal conductivity, and aesthetics that I find really compelling and hard to ignore. The problem, of course, is that in my experience, copper is a material choice that tends to make parts more expensive, especially custom parts, and that can be prohibitive. I started to ask myself like kind of a more realistic question, which is there actually any copper part that I can afford to make? And eventually I found the answer in 3 simple words: sheet metal. Parts. For the DIYson, by using sheet metal and constraining my design to a single plane, I can get a lot of custom copper parts for relatively low cost. Since copper has this high thermal conductivity, I may be able to ditch the heat pipe and merge what was once 2 hard to fit together components into a single component that serves as both the LED support bracket and the means to transfer heat away from the LED. My first inclination is to use the thickest copper sheet that will fit in the rail, which is about 3.2 millimeters. And what I would do is lay it within the channel to maximize the surface area contact between the copper and the aluminum. The problem here is How am I going to attach it to the V-slot rail without drilling holes in the rail? This is something I'd really like to avoid doing, like freehand drilling inside the channel, if I can. It's a little sloppy, hard to reproduce. And after a couple of days or maybe weeks chewing over the problem, I stumbled upon a solution that is just stupidly elegant. The next sheet size down from the 3.2 millimeter thickness is 1.6 millimeters, which just so happens to be the exact size of this cavity in the V-slot rail. If I'm lucky, my part can slide right into this slot, and instead of having to freehand drill a bunch of holes in the rail, what I can do is have holes cut and tapped in the heatsink bracket itself and use a couple of set screws to push the bracket securely against this overhanging part of the channel. This design led me to a phenomenon that I really enjoy. Out of the 78,000 screws on McMaster-Carr, only one of them will perfectly solve this problem and secure the part in place. Since the wheels of the carriage will pass directly over these screws, I think a set screw is my only option. That way there's no head sticking out to interfere with the wheels. Any more than 4 millimeters is also going to stick out through the top, and anything less won't engage with the threads. After filtering it down this far, there's still a couple of options left. But remember, this part is a heatsink after all, and I want to dump as much of the heat I can from the bracket into the aluminum rail. And because of that, I want the most thermally conductive material possible, and in this case, that's brass. So this is my single perfect screw. So I do know that these screws are low profile enough that they won't interfere with the carriage wheels, but I can't say the same for the bracket itself. Space is really tight here, so I feel like I'm trying to thread a needle and just hoping that everything fits. And we're about to find out because the finished parts arrived. I'm really excited about these pre-tapped screw holes along the length of the bracket, and I originally had 10 of these holes because I was kind of into the idea that I wanted to maximize the surface contact between the bracket and the rail as much as I can. And I had this idea that the brass would transfer some of the heat to the aluminum rail. But every tapped hole adds an extra cost, and it was getting a little expensive. So I'm settling for just 6 holes for now. I also opted for these slots instead of holes for the LED holder, just in case in the future I have to swap LED holders. And if I do so, there's still a chance that it'll be compatible with this bracket. And it's the moment of truth, sliding the bracket into the arm to see if it fits, and it fits perfectly. I guess I shouldn't be too surprised because this part is, in theory, the same dimensions as the SuperTrack was, but I don't control the manufacturing. The margin for error here is really small, and yeah, you never know. There's just something about putting the perfect screw in its perfect home. The screws are looking awesome, so the third and final test before I polish this thing up and check out its thermal performance is to get the whole arm up on the lamp and make sure we have enough clearance for the carriage wheels. That's not good. The wheels just catch on the bracket, and while I can roll it over and continue moving the arm back and forth, something really feels off when the wheels are riding on the bracket. And I think it feels weird because the wheels are actually pushed out of the V-slot channel, and instead the flat part of the wheel is rolling right across the top of the bracket. It probably doesn't come across in the video, but the wheels feel more like they're sliding across the surface rather than rolling. And I'm actually a little surprised. I was feeling so confident that this would work. The thing is, the heatsink bracket and the SuperTrack are the same thickness and basically the same dimensions, but there's a key difference, which is that the SuperTrack is screwed down and pulled towards the interior of the track, while this copper bracket is screwed with the set screws and pushed up towards the top. That fraction of a millimeter is the difference between the carriage running smoothly versus getting stuck like we see here. I feel kind of stupid for rushing forward and ordering this part without taking the 20 minutes of time it would take to do a 3D printed test part, but here we are. So how do we solve this problem? Making the heat bracket uniformly thinner by sanding off like a few tenths of a millimeter won't help us here because no matter how thin the piece is, this face will always be in the same place and will always interfere with the wheels. What I could do is somehow shave off material just inside the channel here using something like a Dremel tool, but it's not something I feel comfortable asking anyone who wants to make the DIYson in the future to perform because it's just kind of a messy task. What I could do is take off a uniform amount of material and then use a copper strip on each side to create some distance between the bracket surface and the wheels. But again, this feels demanding, overly tool dependent, and I just don't feel good having this as a required assembly step. It feels like I'm so close and I'm not ready to give up on the idea of a laser cut copper bracket yet. I know the issue is the bracket pressing directly up against this face, causing just enough clearance issues. But I wonder how the math works out if I go back to my original plan and instead fasten the bracket to this interior face. Looking at this area, I have a bit more space to work with, roughly 4.3 millimeters. I have to make the whole bracket a lot narrower to fit in the crevice, so I also want to compensate for the loss of strength by increasing the bracket thickness. The next size up from 1.6 millimeters is 3.2, actually more like 3.18, which leaves us with 1.1 millimeters of space for a screw that can hold the bracket in, which means it's time to play the fastener filtering game again and see if there's a perfect screw for this application. What I need is an M3 6mm long screw with a super low profile head, no taller than 1 millimeter. And it looks like we found our screw, and at only $3.85 per screw, they're one heck of a deal. They're such a good deal that I'm going to reduce the number of required screws by half so the entire DIYson budget doesn't go directly into capitalizing on this deal. Using these screws with a thicker plate, I'm left with just 0.1 millimeters to spare. That's pretty tight, though to be fair, the copper plate is technically 3.18 millimeters, not 3.2, so I guess I'm left with 0.12 millimeters. Ugh. I'm going to try to learn from past mistakes for once, and using the super low profile screws, I'm going to print off a stand-in prototype for the bracket before I order the final part. The printed part seems to fit, but it's a little ambiguous because the difference comes down to just like a few degrees of rotation of the screw, and I worry that the reason it fits now is because I'm just slightly compressing the 3D printed part when I'm tightening the screw the last little bit. I guess I won't know until I put it to the test with the metal part. And actually, before I order the new part, as I was designing it, I couldn't shake the thought that I should try everything I can do to make the heat pipe solution work. So in the same batch of parts, I'm including this short little copper bracket, which features a 90-degree bend and connects to the front of the arm. It has this little cutout here that I'm hoping I can somehow thread the heat pipe through, even if that means I have to do a little bending of the heat pipe. I just really want the heat pipe to work. After a few days, the new brackets arrived, and the bend in the heat pipe bracket looks perfect. And I really like the heft of the new thicker heatsink bracket. These both look promising. Let's take a look at the heatsink bracket and I'll show you how I plan to drill the mounting holes in the aluminum rail. I made this little guide that helps me drill straight holes in the right places. The first piece slides into the rail, and when I align this face to the end of the rail and then slide my little hole guide in, this hole guide is positioned right where I need my first hole. After drilling the first hole, I can tap it, screw the bracket in place, and then use the bracket itself to align the final two holes. Unfortunately, I only bought 2 of these really expensive ultra low profile screws and I lost one, so I only have one left to test the bracket with, so I'll have to make do. Putting the whole assembly together on the arm, I'm holding my breath because the margin of error here is like 0.1 millimeters, and I'm just hoping that it's enough to clear the carriage wheels this time. It seems like it's the same story as with the previous attempt. I'm over by a fraction of a millimeter, and the wheel is just catching on the edge of the screw. But I noticed something interesting. If you look really closely at the wheel, only one edge is actually hitting the screw, and the wheel itself is just slightly skewed. This is happening because the 3D printed carriage gets a bit warped when the eccentric spacers are tightened, but up until this point it hasn't really been an issue because I hadn't been working with tiny tolerances. Now it's really apparent. I wonder if I use a more rigid carriage like the one Jake Brownson made for me a while ago, maybe that would fix the problem. And it turns out this works. The wheels just clear the top of the screw, kind of like I had expected from my calculations, and the motion is super smooth. Okay, let's put a pin in the heatsink bracket for now, and I want to test out the 90-degree bracket solution. I just need to check that the heat pipe fits through the hole, sits flush with the top of the bracket, and aligns with the interior of the rail. And this looks just about perfect. It looks like out of the box, it's just going to work. I'm at a point now where I see 2 paths forward. One is with this, the heatsink bracket, which is a solution that's really close to working. I either need to just shave off a little bit of the surface or stiffen up the carriage so that it doesn't flex, or maybe even potentially finding some even lower profile screws that don't interfere with the carriage wheels. It's pretty close. But the 90-degree bracket is even closer. It already works. The only problem with this bent bracket is that I've grown somewhat infatuated with the heatsink bracket and the fact that it's a single piece, and I really want to make this work. Right now, I feel pretty much split right down the middle between these 2 solutions and feeling really stuck. but I have an idea that should help me get unstuck. I want to do an experiment that puts heat pipe against heat sink bracket and compares their cooling performance. Will they keep the LED cool enough? Which one will cool it better? Will either of them cool it enough to stop the plastic housing from melting? I don't know the answer to any of these, and this is what I want to learn from the experiment. What I'm hoping for is that the heat pipe solution performs so much better than the heatsink bracket that I basically can't ignore the thermal advantages of going with a heat pipe, and my hard decision is basically just made for me, and I end up using the heat pipe on the DIYson. Why do I think this heat pipe will do so much better? It's because even though on the surface these are both copper components, heat pipes are more than just pipe-shaped pieces of copper. Inside the pipe, there's a small amount of water, and it's under a vacuum. When that water heats up, it changes state from liquid to vapor, creating a pressure differential between the hot end of the pipe and the cooler end. The hot vapor rushes to the other cooler and lower pressure end of the pipe, where it cools, condenses back into its liquid state, and then works its way back to the warm end of the pipe through this meshy, kind of spongy area called the wick. Then that cycle just repeats over and over. Through this process, the heat pipe can move energy from one end of the pipe way faster than a solid piece of copper, and that's its advantage. It transfers heat really effectively. And fast. So I want to do an experiment to understand just how effectively the heat pipe transfers heat relative to the solid copper of the heatsink bracket. I'll have two setups, one with a solid heatsink bracket and one with a heat pipe. I'll set up 5 temperature sensors at key points on the lamp: the LED chip, the interior of the LED housing, 100 millimeters down the cooler, 200 millimeters down the cooler, and on top of the aluminum rail. I'll power up the LED to 30% of its max brightness, and I'll record the temperature readings every 30 seconds from all 5 sensors for 30 minutes. That should give us enough data to see how well each solution pulls heat away from the LED and dumps it into the aluminum rail. My prediction is that the heat pipe solution is going to totally crush the solid copper in the heatsink bracket. I think the heat pipe is going to just suck up all the heat from the LED and then dump it into the aluminum rail. And the aluminum rail is going to get warmer in that experiment, but because the amount of energy between both experiments is the same, a warmer aluminum rail should equal a cooler LED. And if that happens, it's going to make my choice really easy. What I'm hoping for now is just that the difference between the heat pipe and the heatsink bracket is so big that it's a no-brainer. I don't want it to be ambiguous. So that's what I'm hoping for. So I've had the first experiment running for a couple of minutes now, and I just wanted to show you the setup that I had. So I have all my sensors hooked up here on the lamp, plugged into these two thermometers. Well, one's a multimeter and one's a thermometer. And the way that I'm capturing the data every 30 seconds is that I just have my phone set up to take a snapshot of the screens on the thermometers every 30 seconds. There, just took one. And then once the 30 minutes is over, I'll take all those images and I'll use them as the source of my data, and then I can do some analysis on that data. So now it's just time to wait. All right, so I have some data now, and the only change I made to the experiments is that I ran them for an hour each rather than just 30 minutes. And that's because I wanted to make sure that the LED got to like an equilibrium temperature where it was starting to level off and stop increasing. And 30 minutes just was just under that plateau for both of them. So I doubled the length, which also doubled the number of data points. So now we have like a nice big number of 1,200 data points that we're seeing on the screen here. So let's take a look at it. These two graphs show the sensor readings over time for both the heat pipe solution on the left and then the heat sink bracket solution, like the solid copper solution on the right. And one of the things that I noticed right off the bat that I want to point out is the average sensor temperature between both tests is very close. It's just a difference of 1.5 degrees Celsius. And that's consistent with kind of the hypothesis that we had going in, which is that we're observing two solutions that should have the same energy output roughly. So anyway, looking at the two graphs, the heat pipe is the obvious winner right off the bat, but there's a couple of subtle things that I wanted to point out. I say it's the obvious winner because the LED temperature is just lower. You can see that in this yellow line here. Not only is the max temperature lower, it's hovering right above 70 degrees Celsius, maybe a little bit more, like 72. Whereas the solid copper bracket is into the 80s, like mid 80s, 85 by the time it gets to the end. But not only that, the heat pipe solution arrives at that max temperature a lot more slowly and more gradually. So it's much more controlled than the heat pipe solution. Whereas with the solid copper solution, it just shoots right up. Like by the time you're 3 minutes in, it's already at 70 degrees. Whereas the heat pipe solution really is controlled. It takes a long time to get to 70 degrees. Like it's not hitting the 70 degree mark until 28 minutes in. So that temperature is changing much more gradually in the heat pipe solution. And the reason it's changing more gradually is also illustrated in this graph. So not only is the LED temperature lower, so like that extreme high temperature is lower, the extreme low temperature is also higher. And what I mean by that is all the other components in the lamp, things that are hooked up to these sensors, are bumped up on this heat pipe solution. So they're all raised up, and that's because the energy that's coming off of the LED is being absorbed by these components in the heat pipe test, where the heatsink bracket, the solid bracket, isn't really seeing that. Like you have these areas of really low temperature where it's just not really doing anything to help with cooling. And so the result of that is the solid copper bracket has these extreme highs and extreme lows, and it's just not working as like a cooling system. It's just a bunch of metal, and it's all, I don't know, sometimes it's absorbing heat and sometimes it's not. But there are also some surprises in this data. I think what you would expect from a setup like this is that starting from the heat source, the LED chip, the temperature is going to be very high, and then gradually as you get farther away, the temperature will get lower and lower as you move away from the heat source. But if you look at this data, it's actually for the heat pipe solution, the results are the inverse. So obviously like the LED chip is the hottest, like there's no way around that. It's almost always going to be the hottest component unless I come up with like some crazy efficient solution. But the second hottest sensor on this setup is 200 millimeters down the heat pipe on the opposite end of the rail from the LED. So this is the sensor that's farthest away from the LED, and it's actually the hottest. And as you get closer to the LED, things cool down. So the next hottest component is 100 millimeters down the heat pipe. So it's getting closer to the LED. And then the next is the rail. So that is right around the same point as this blue line, but it's touching the rail rather than the copper itself. So that makes sense that it's lower. And then the coolest area on the whole setup is the ambient air around the LED inside the housing. That's amazing. So the heat pipe is just like sucking the heat out and actually just dumping it as far away from the LED as possible. So that's like the ideal solution. I did not expect this to happen. This is more of what I expected to happen, the solid copper solution, where the LED is really hot, things close to the LED are hot, but as you get further away, like 200 millimeters down the bracket, like this pink line here, that's when things start to actually get a little bit cool. This is what I expected, but the heat pipe does crazy stuff. It just moves heat like magic. But then at the end of the day, looking at both of these experiments, specifically looking at the average ambient air temperature around the LED, which is the average housing temperature, both of these are quite low. Like 43.5 for the solid heatsink bracket experiment is still well below what I would expect a temperature that would cause like warping or melting of the plastic. So in theory, like both of these could be used. The average LED temperature between them is also both within the limits of the LED chip. But also, thankfully, looking at these, there's a clear winner between these two because the heat pipe is sucking heat away from the LED so efficiently that it's able to operate at a significantly lower temperature, which is going to increase efficiency, and it's just doing all the things that I want, and the solid copper heat pipe is falling behind. So even though there's a lot of things I like about that solution, like the construction and the elegance, the heat pipe is the clear winner. So I'm going to go with that. Here's the heat pipe setup through a thermal camera, and the horizontal arm here is glowing consistently across the entire length, which means we're seeing similar temperature across that arm. The heat pipe here is basically allowing the aluminum rail to function as a giant heatsink, pulling heat away from the LED and dissipating it into the air through the large surface area of the rail. In the test using the solid copper bracket, the heat isn't really spreading. There's an obvious concentration of heat around the LED, but the temperature of the aluminum rails drops drastically the farther it is from the LED. Big thanks to Kiran for letting me borrow this thermal imaging camera. It's really cool. And I'm really happy with this result. I basically went from having this really tough decision that I didn't feel equipped to make to having a bunch of data that basically forced me to choose the best solution, and that is the heat pipe. And while the final version does need a little bit of refinement, I think it's really close, and it's close enough that I can start to do some real world testing like I mentioned earlier on in this video. So I can combine the heat pipe solution as it is now with the SuperTrack, and I can finally use it just like a normal desk task light. And by doing that, I can learn more about the reliability and practicality of using the SuperTrack solution long term, like moving it around, really stress testing it, seeing if it works. So that's what I'm going to do. And once I have some findings, I'll make sure to share them with you. I also have a couple of other improvements that I want to make to the DIYson that are in the queue. And once I have something to share, I'll put a build log together and I'll share it with you. I want to make build logs with a little bit more frequency and regularity, but honestly, I don't know how people make videos so fast. I'm really slow at it, so I appreciate your patience as I'm getting these videos out. I'll share with you as soon as I can, and until then, thank you for watching, thanks for your support, and I'll see you in the next one.